An ancient monster, invisible yet all-powerful, has just released a cosmic scream brighter than 10 trillion suns.
A distant galaxy, a familiar supermassive black hole, another scheduled target in the James Webb Space Telescope's long queue of cosmic heavyweights. No one expected surprises. The models were solid, the mass had been estimated, the accretion rate seemed stable. Webb locked on. The exposure began. At first, the data looked clean. Then the timing shifted. A flare rose sharply from the inner disk. Nothing unusual there. Accretion disks are violent places. But seconds later, a second signal appeared. Delayed, redshifted, coming from an angle that didn't make sense. That's when the room went quiet. Because just minutes after NASA pointed JWST at that black hole, they started deeply regretting it. Not because Earth was in danger, but because the data suggested something far more uncomfortable. The black hole wasn't behaving conservatively. It was operating near the absolute limits of space-time itself. And that meant the models they trusted might be standing on thinner ground than anyone realized. Black holes are not cosmic vacuum cleaners in the cartoon sense. They are predictions, consequences of Einstein's theory of general relativity. When a massive star collapses and no force remains strong enough to resist gravity, space-time itself caves inward. If the mass is sufficient, the collapse continues until a region forms where escape velocity exceeds the speed of light. That boundary is called the event horizon. Cross it, and no signal can return. For decades, the event horizon has been treated as absolute, a perfect divider between the observable universe and whatever lies beyond. We cannot see inside it. We can only study how matter behaves near it. That's what Webb was designed to do better than any instrument before it. The James Webb Space Telescope sees in infrared wavelengths, allowing it to penetrate dense clouds of gas and dust that obscure galactic centers. At the heart of many galaxies sit supermassive black holes, millions or even billions of times the mass of our Sun, surrounded by glowing disks of infalling matter. As gas spirals inward, it heats to extraordinary temperatures, forming an accretion disk. Above the disk lies a region called the corona, where magnetic fields twist violently and emit powerful radiation. These regions are chaotic. Variability is expected. Flares are expected. What wasn't expected was the timing pattern Webb recorded. A burst of emission rose sharply from the inner disk. Seconds later, a second signal appeared, fainter, redshifted, delayed in a way that implied a longer path through curved space-time. At first, this seemed like standard gravitational lensing. Einstein predicted that gravity bends light. Near a black hole, this bending becomes extreme. Photons can curve around the event horizon before escaping. But when the team mapped the geometry, something didn't align. The reflected radiation appeared to originate from a region that should have been hidden behind the black hole, not inside it, but geometrically blocked from view. And yet, it was visible. That alone wasn't impossible, but the structure of the signal made it harder to dismiss. It wasn't random scatter. It carried coherence, which meant the inner disk was behaving in a highly organized way, very close to the event horizon, closer than most models predicted. Then came the spin calculation. Black holes can rotate, and when they rotate, space-time itself is dragged around them. This effect, called frame dragging, changes the structure of the region near the event horizon. In rotating black holes, described by the Kerr solution to Einstein's equations, the innermost stable orbit for matter moves closer to the horizon as spin increases. The faster the spin, the deeper matter can orbit before plunging inward. Webb's spectral data showed extreme broadening of iron emission lines in the disk. That broadening is a fingerprint of relativistic motion. The numbers suggested something startling. The black hole was spinning near its theoretical maximum. Near maximal spin changes everything. It shrinks the stable orbital radius. It enhances energy extraction. It amplifies magnetic field interactions. And it pushes space-time geometry toward its most extreme allowed configuration. At that spin rate, the inner edge of the accretion disk lies almost on top of the event horizon. That means radiation emitted from that region experiences enormous gravitational distortion. Light paths twist, time dilates, energy shifts dramatically. The delayed echo Webb captured was consistent with this extreme geometry. But the precision of the data revealed something else. The magnetic fields near the black hole appeared highly ordered, not chaotic, structured, and that suggested efficient energy transfer between the spinning spacetime and the surrounding plasma. One theoretical mechanism explains this, the Blandford-Znajek process. In this model, rotational energy from a spinning black hole can be extracted through magnetic fields, powering jets and accelerating particles to near-light speeds. This black hole was not previously classified as a major jet producer, yet the flare pattern hinted at transitional behavior. That raised the stakes.
There was no danger to Earth. The black hole lies hundreds of millions of light years away. The regret wasn't fear of destruction, it was intellectual discomfort. The models had assumed moderate spin, stable disk geometry, predictable variability. Instead, Webb revealed the black hole operating at the edge of theoretical limits. And when physics approaches its limits, small uncertainties grow large. Black holes sit at the intersection of two pillars of modern science. General relativity describes gravity and curved spacetime. Quantum mechanics governs the smallest scales of reality. Both work extraordinarily well, but at the center of a black hole, relativity predicts a singularity, a point of infinite density. Quantum theory refuses to accept infinities. That contradiction remains unresolved. Webb did not solve it, but it pushed observational evidence closer to that boundary than ever before. When the inner disk brushes against the event horizon at near maximal spin, we are observing spacetime under conditions that test the limits of relativity itself. And so far, Einstein still holds, but barely.
The polarization data added another layer. Subtle shifts in polarization revealed the orientation of magnetic fields near the horizon. They were twisted, aligned with frame-dragging predictions, meaning space-time rotation was actively influencing plasma structure. That level of coupling suggests an efficiency in energy extraction that approaches theoretical maximums. In other words, this black hole wasn't quiet, it was operating with near-perfect gravitational efficiency. That's rare, and it complicates assumptions about black hole growth and galaxy evolution. Minutes after Webb began transmitting those datasets, scientists weren't panicking, they were recalculating, refining spin parameters, rerunning ray tracing simulations, testing stability thresholds. Because when you observe a black hole this close to its theoretical extremes, you don't celebrate, you double-check. The regret wasn't about pointing Webb at the object, it was about realizing how much more extreme reality can be than our models assume.
Black holes were once thought to be simple. Mass, spin, charge. 3 numbers, that's all. But the more precisely we observe them, the more complexity emerges. Disk turbulence, magnetic reconnection, relativistic jets, frame dragging, structured variability. Webb didn't reveal what lies inside the event horizon, it revealed how violently intricate the boundary itself can be. And that boundary is where the deepest questions live. Does information survive? Is the singularity real? Does quantum gravity soften the collapse? We still don't know, but we are closer than ever to testing those questions observationally. Just minutes after NASA pointed JWST at that black hole, the data forced them to confront something uncomfortable. Nature is willing to push gravity to its absolute limits. And when gravity approaches those limits, our confidence in neat, stable models begins to waver. Not because physics is broken, but because it is deeper than we imagined. The black hole didn't threaten Earth. It didn't emit some forbidden signal. It simply showed us what space-time looks like when it is stretched to the edge of what reality allows. And that may be even more unsettling, because it means the universe is not conservative. It is extreme, and we have only just begun to measure how extreme it can become.